Alright, ladies and gentlemen, today we will be discussing section 4.6, isosceles and equilateral triangles. I'm pretty sure that's somewhere in Florida. Now, we all know what an isosceles triangle is. We've defined it before. When we talk about an isosceles triangle, excuse me, specifically we are talking about a triangle that has two congruent legs. When we say an equilateral is a special case for an isosceles triangle, that's just basically so that we can apply all the special rules for isosceles triangles to an equilateral triangle. So in an isosceles triangle, we have our definitions here, and remember, pause and take notes as you need to. The legs of the isosceles triangle are the two congruent sides of the triangle. The base is the third side that is different. The vertex angle is opposite the base. It is formed by the intersection of the two legs, and the two congruent base angles are formed each by an intersection of one leg and one base. Each base angle is opposite one of the legs. Now, isosceles triangle theorem basically says if you've got two congruent sides, then you've got two congruent angles. Similarly, the converse says if you've got two congruent angles, then you've got two congruent sides. So we have our statement here, if AB congruent to BC, then angle A is congruent to angle C. Or the converse, if angle A is congruent to angle C, then AB is congruent to BC. So basically we're going to prove it. So let's go through, we'll set it up. We know how we set this up. The first thing is always the given, so we'll just put that right in. Okay. And we'll mark our two sides as being congruent. Now we're going to do something we've never seen before. We're going to start adding things to a diagram. Now, every side of a triangle is a line segment. So what that means is that every line segment can be cut in half because every line segment has a measure. So we're going to basically just take our base, which is AC, and we're going to say, hey, it's got a midpoint. And we're just going to call that midpoint X. All right? Okay, so now we have our midpoint, so we're going to say, hey, you know what? We're going to draw our line segment BX. And you're going to say, wow, you can just draw line segments in? Yes, you can just draw line segments in, because if you think back to your first postulate that you wrote down, all right, it says that every 2 points determine a line. So, yeah. Now, this is what's called an auxiliary line. Some people like to draw it in as a dotted line so that it looks different. Others don't care. They just draw it into the diagram regardless. So now what I've done is I've taken this isosceles triangle and I've split it into two triangles. So because I know that X is a midpoint, I get to say that AX is congruent to XC because of midpoint theorem. I'll of course mark that. And thanks to reflexive, which now we know is actually useful, we get to say that BX is congruent to BX. So now I know that these two smaller triangles are congruent to one another. Be careful of how you choose to name them. Remember, you have to be consistent in naming the corresponding parts. And of course, once we name two triangles as congruent, we can pick out the sides with CPCTC. Now, once we stop dealing with the idea of just isosceles triangles when we start talking about equilateral triangles, we say that we have a couple corollaries, and these basically derive from isosceles triangle theorem. So if a triangle is equilateral, it's equiangular. We already knew that. Now we're just saying that there's a theorem that basically says it. Remember, the only reason, and I said this just a minute ago, the only reason that we bother to say, hey, you know, an equilateral triangle is basically a special case of an isosceles triangle is so we can say, hey, every rule that applies to isosceles triangles also applies to this. So that's why we bother to go through that. Oh, that was strange. All right, so basic calculations. We want to find the measure of angle SRT. So let's start by writing down what we know. And the truth is, the only thing we know is that this is a triangle and that all the angles in a triangle add up to 180. But because of those two congruent marks on segments ST and TR, I know this is an isosceles triangle, And I know, thanks to isosceles triangle theorem and its converse, basically two congruent sides, two congruent angles. So if the legs are congruent, the base angles are congruent. So I know that angle RST and SRT are congruent, therefore their measures are equal. Okay, and I know that that vertex angle up there, TSR, is 50. So I plug in, I clean up. Now I chose to replace RST with SRT. It would have worked just as easily the other way, but I was trying to find the measure of angle SRT. That's why I decided to use it. So, little substitution property. We're going to combine those measure of angle SRTs together. We're going to plug in our 50 for TSR, subtract from both sides, and we get the measure of angle SRT is 65. Very simple, very straightforward. Now, if I take the exact same approach, notice I changed the angle to 52 degrees from the last diagram. But if I take the exact same approach, I can start off by saying the exact same thing. Okay, when I add up all the angles, I get 180. And I know that the measure of angle STR is 52. That's how it's labeled. And the other thing is now I have actual quantities that are labeled for angle TSR and angle TRS. Excuse me. And because this is an isosceles triangle, I do still know that the measure of those angles are equal. So once again, I just kind of write out what I know. Put the two measure of angle SRTs together. Plug in. Clean up. We get y is equal to 11. Now remember, we have to find the measure of both variables, and since we're lucky enough to know that 4x plus 20 equals 6y minus 2, I plug in what I know. All right, no need to move that variable over. We'll just kind of work with it where it is there. And we get x is equal to 11. Now, of course, it's completely unnecessary for us to plug back in order to find the measure of those angles, because we could just say, hey, 180 minus 52, and then divide that by 2. So that's not a necessary process for us right now. All right, here is the long one. Try and follow along. It is a proof, and it is complicated. I'm just going to move that text over so we can get rid of the example 4, and I'm going to start setting that up there. Obviously, we'll start with our given. Label what we know. Alright, that's the first time I ever tried pausing a recording. Looks like it didn't cause any problems. So the only thing we can really do from our given is label those two sides as parallel. Now, by telling us that the hexagon is a regular polygon, we know that regular polygons are both equilateral and equiangular. So what that means, so because we know that, we can now jump in and we can say, okay, well, let's start marking all those sides as congruent. And it's not a big deal. It's just a bunch of tick marks. Okay. And the other thing we can do is because of the fact that they tell us that triangle ONG is equilateral, that means we can label all the sides of triangle ONG as being congruent and all the angles of triangle ONG as being congruent. And that's just because of the definition of an equilateral triangle. Well, when we start labeling the sides, we've already got one tick mark on side OG, so that means we're going to be labeling the other ones with one tick mark as well. And I just happen to use two arc marks to label the angle. It's not really anything special. And we're still not quite done here, right? Now we're doing good. Okay. Now, what happens is when we look at this, angle OGN and angle XEN are congruent because if we take a look at the diagram, remember that's angles OGN and XEN, they are actually alternate interior angles. And that's because of those two sides being labeled parallel that we can say that. All right, and I kind of went out of order a little bit because really I should have said that GN is congruent to NE first because that does derive from the midpoint, from saying N is the midpoint of GE. So I kind of jumped the gun a little bit on that one. Well, remember, our whole goal is to prove that triangle ENX is equilateral. But if we look at triangle ENX, we see side angle side, and we also have side angle side on triangle ONG. So that means we can say that they're congruent through side angle side. And of course, that means the missing pieces, angle ENX, angle EXN, and side NX can all be labeled as congruent to their corresponding parts in triangle ONG. And, excuse me, we can, of course, use CPCTC. And, of course, once I label that, and I see that my sides are all congruent and my angles are all congruent, well, clearly, I have this statement. Now, this is where things get a little difficult. When you have all these congruent marks all over the place, and people start saying, well, whoa, 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 how can you say this is congruent to this? I mean, yeah, I see it on the picture, but what's my actual reason? Anytime you see this, where you just have these congruent marks all over the place and you're picking things out, what's actually going on is you are using the transitive property to skip over pieces of information in a larger congruent statement. So that is an acceptable reason. Now, of course, once all three sides are congruent and once all three angles are congruent, we can say that we do have an equilateral triangle, and our reason would simply be the definition of an equilateral triangle. So, hopefully you paused, you wrote things down. I realize it's a little hard to see proofs in a video, especially when you're moving through them somewhat quickly. I did try to explain every step, so we can discuss anything that we have to the next time we see you in class. So remember, you're responsible for the homework associated with this section, and good luck.